Unit 18, Part 10, I'll do a theorem before I get to the model universe proof of an argument's invalidity. Before that, just notice this will be the point from page 347, top of 347 of Klenk. Remember that universal instantiation and existential generalization are unrestricted rules, right? And universal generalization and existential instantiation are restricted rules that require flagging. Look how that manifests itself in relational predicate logic. Look at this difference. Notice that we can make an inference like the top one here. This is for all, so L, X, Y, X loves Y, A for Anne. This is for all X, X loves Anne. Everybody loves Anne, the name A-N-N, right? We are indeed entitled to infer from everybody loves Anne, this universally quantified statement. Since it's a universally quantified statement, we are allowed to infer that Anne loves Anne, right? It's a valid inference. If it's true that everybody loves Anne, it's also true that Anne loves herself, right? She is a person, so that's a valid inference. Notice that we cannot make the proof in the bottom one. Hey mate, wanna come say hi? Come on. This is, you wanna point to these? This is TXA, that is, say hi. Hi. Is your birthday tomorrow? Yes. How old are you? 4. Cool, give me a kiss. Okay. Why don't you stand there and point to it and you can be on camera. Point like this. This says there exists an X such that X is taller than Anne, right? So this is the symbolization of somebody is taller than Anne. Okay. It would be clearly an invalid inference to infer from that Anne is taller than herself, right? We would be going from something true to something false, right? True that someone's taller than Anne, not true that Anne is taller than herself, right? Notice how the restriction on existential instantiation, right? Existential instantiation is a restricted rule. It is a flag rule. It prevents us from making this inference. Happily prevents us from making this inference because it's an invalid inference. Look back to Unit 15. The motivation for these restrictions was it would prevent us, if the restrictions were required, because otherwise the rules would be invalid. They would allow us to move in our thinking from things that are true to things that are not necessarily true. Okay, so see how it's restricted, right? Someone is taller than Anne, therefore Anne is taller than herself. What is this? What is this here? Sorry. TAA, right. Anne is taller than herself. This would be an existential instantiation, right? And we would have to, right, A for X, we would have to write flag A, and we would have broken the flagging rules. A has already appeared in the proof here, right? In fact, we've broken 2 of the flagging rules. The letter A has already appeared in the proof, and secondly, it appears in a premise. The second rule for flag letters is the flag letter may not appear in the premises or conclusion. All right, they say a bit more about the restrictions on the flag rules, including here in relational predicate logic, the third rule that the flag letter may not appear outside the subproof in which it is flagged comes into play. We'll talk about that, but I'm not going to say much about that. I won't say anything else about that. Let me move on, don't kick that over, to theorems. Okay, theorems in relational predicate logic. There's nothing new, really, to the use of theorems. It's just a little bit more complication in the application of the thing. So this is example, it's 354, page 354 in the exercises. 2C, it's a comma. Example 2C I'm going to do, right? So I'm going to do this exercise sheet. Klenk works through a couple in the text. Have a look at those, make sure you follow them. But this is the theorem I'm going to do. So I just graded your second exams, and not everyone did this, so I'll say it again. What do you do with theorems? That's alternate names of P for page. Right? P for page number. Page 354 is what it says. You have to, you're presented with a formula, you're asked to prove this theorem. What do you do with that formula? You draw a line and you put it at the bottom of the proof, because you are not given that formula as if it is a premise or anything like that. So don't write a line and put 1 and write the formula down. Put it down the bottom. You are asked to prove it, right? It's a theorem. Theorems are formulas proven with no premises. A proof of a theorem always begins with an assumption, right? So you let the structure of your conclusion, conclusion, which is the formula now, right? You see it as the conclusion if you do the right thing and put it down the bottom. You let the structure of this formula determine what the assumption is you're going to make. You're going to make an assumption. So the new thing, something new in relational predicate logic, is that assumption might be a flagging step, right? If this is a universal statement, then the first step will be flagging step, flag A, flagging step for universal generalization, derive a certain instance, and then do a universal generalization. Pause the video and answer the question, right? Analyze the form of this very carefully and tell me, what is the form of this formula? I'm about to pause it myself. Okay, welcome back. Is this a universal statement? Right? 2 conditions for being in quantifier form. Begins with a quantifier. Yes, it does. Second condition, scope of the initial quantifier has to go all the way to the end. It does not. This is not a universal statement. Very, my point, I'm saying this, very important to pay close attention to the form, to the arrangement of the brackets to determine the form correctly. Right? This is in fact a conditional, right? It's this bracket, right, binds 2 open brackets, 1 closed bracket, that's for the quantifier. And when you get to here, that's the formula that's bound, that's the formula that this universal quantifier binds. So this is a conditional, and this universal statement is the antecedent. It's conditional, so I'm going to set up for conditional proof. Yes, mate? That's for pointing and stuff? You can point to that. Okay, so I put the antecedent up the top. So my assumption is assumption for conditional proof. And again, gx, right? Notice the form of that, right? It's a conditional with the, this is a conditional, and it's a conditional, not an existential statement. I'm sorry. It's a conditional, and what, mate? Recording? Yeah, that's right. Thanks. Right? Yeah, that's it. Right. It's not an existential. It's not an existential formula. Scope of the EX goes just to there. Right. It's a conditional. That's the antecedent. Put the consequent down the bottom. It is for all x, for all y, fx hook g y. All right. So you're off. You put the thing down the bottom. Good. Form determines your move. It's a conditional. Antecedent consequent, and you're off. You've got this premise, and you have to derive this somehow from this. And if you do so, you're entitled to infer if that, if this, then that. Q. Conditional proof is the justification for the conclusion. All right. Excuse me, please. All right. So now, let the form determine your move. What is this? What is the form of this? Is this a quantifier statement? Yes, you're right. It is. Scope of this goes all the way to the end. So I'm going to set up I'm going to flag. I'm setting up a flagging subproof for universal generalization, right? And this flag A notice that this is a conditional, right? So what am I doing with this? I'm not sure. I'm thinking modus ponens and modus tollens, I have to be thinking. How am I going to do modus ponens and modus tollens? Okay, let me keep working backwards and see what appears, and I should be able to figure out. Look, you're getting chalk all over the place, mate, and all over your thing, and you bathed, okay? Don't put your hands on the wall, please. Thank you. That's my formula. what is the instance? Okay, the variable y stays in place, right? Doing the reverse of universal instantiation.
When you finish with this, can I watch the philosophy movie?
You can watch the philosophy movie after we finish. Yeah, you can see yourself. I'll show you. Fx. Nope. The x becomes a. Don't touch the wall, mate. You're messing up. You can only watch if you don't touch the wall. Don't touch. Okay, it's fa. Fa hook gy. The y remains in place. Right? Will x fx of gy. Sorry, fx y. Yeah. This is fxy, so that's fxy. So that becomes fay of gy. Good. Okay, that's what we want. What's this form? This is a universal statement, right? So we write flag B, yeah, flag B, flagging step for UG. I flagged A, so now I've got a flag B. This has got to be B. It's going to be a B flag subproof, so this determines, right, I'm instantiating in reverse, as it were, F, replace all the Y's with B, the A's remain A's, so it's FAB, hook, G, B, right? This is going to be UG, and that's going to be UG, and this is going to be CP, of course, right? Okay, so now I've got this. This is a conditional. Let me set up a conditional proof. G, B, F, A, B. Okay. So what? What have I done wrong?
You did that one.
Just a Y. That's something wrong. Oh no. X, Y, G, Y. No, okay. So oh, I have done something wrong. Yeah, this is FAB. So just a Y. Resolve my confusion and come back. I'm sorry.